Hey guys, it's Mr. Bison here. You know the score with these things. I'm going to be doing everything you need to know for FP1. And this has got a lot of stuff from the formula book here. And I just want to say at the very beginning, this is not going to replace being able to do practice on these questions. Some of the sections, like conics and reducible differential equations, there are so many things that you'll learn from just practicing questions. So this is just good to give you like a kind of a broad overview. And you can see it's pretty dense. It's a lot more dense than Further Mechanics 1 and Further Stats 1, because there's a lot going on in this module. So we're going to begin with chapter 1, which is vectors that we've got here. And if I say FB, it means that it's in the formula book. So some standard definitions. First of all, for the cross product, although this is in the formula book, I think I probably would know this one by heart. It's the modulus of the A vector, the modulus of the B vector, multiplied by sine theta times by the n vector as a unit vector that we've got there. Now remember that n just means that it is going to be perpendicular to both of these vectors. Now if we do b cross a is not exactly the same as a cross b. It's actually the same as minus a cross b, and that can sometimes be useful. Now this is in the formula book about how you actually evaluate an a cross b that we've got here. You do the determinant of this 3x3 matrix where you put the a vector going across and the b vector going across here. So I've got it a1, a2, a3 representing a, of course. I don't memorize this, I use this one, but this is the equivalent form of finding the determinant of this 3x3 matrix that we've got here. Now the triple scalar product is defined as a dot b crossed with c. Again, this is in the formula book, so I've just got it pre-filled, and it's literally just the determinant of the 3x3 matrix where you put a, b, and c like this. Now, this is something that is also in the formula book, but I want to go a little bit more explanation. If the letter order is the same, and when I'm saying the order, I mean the way that you would read it from left to right, and I'll explain a little bit more in just a second. If it is the same, the result is equal. So this thing is in the formula book that we've got here. And what I mean by the letter order being the same, if it goes A, B, C, A, B, C, A, B, C, you can see here that we have B, C, A, and actually B, C, A is a section that we've got here. There is B, C, A. So if I was going to try and show one that is not the same, well, I could go like backwards and I could say C, B, A, or maybe A, C, B. I think the one I was going to go for with the C, B, A. So this is not equal to C dotted with B cross A. And the reason it's not equal to is because if you read to the right, you can only see C, A, B. You can't see C, B, A there. So for some geometric uses that we've got for this, we've got a parallelogram, a triangle, a parallelepiped, and a tetrahedron. And so for the area of a parallelogram, where we have the two vectors are coming from the same point of the two sort of parallel sides, or the ones that aren't parallel but have the pairs of parallel sides, to find the area of a parallelogram, it is just the modulus of A cross B. Obviously, you could do B cross A because you're taking the modulus as well. For the triangle, it's actually half of a parallelogram, so it is just a half of A cross B. Now, the volume of a parallelepiped is like a cuboid where all of the sides are parallelograms. It would also work for a cuboid. They all have to be coming out of the same point that we've got here. So we have A, B, and C, and they could be shuffled around in any order. It is just going to be the magnitude of A dotted with B cross C that we've got. And then for the volume of a tetrahedron, it is the same as a parallelepiped, but it's a sixth of it, which tells you that 6 of those tetrahedrons would make a parallelepiped. A tetrahedron is a 3D shape where all of the sides are triangles. Careful, they have done some shapes before where they're not all triangles and you have to break it down in other kinds of ways. And then geometrically, if we have two vectors that are parallel, then A cross B, not even, the magnitude, I don't think we want the magnitude there, A cross B is just equal to 0 that we've got, okay? And that makes sense when you look at this definition that we've got. If they are parallel to each other, then theta would be 0, and sine of 0 is 0, so the whole thing that we've got there is 0. That's everything that's there from the year 1 stuff, and now this stuff to do with lines and planes is for year 2. So the equation of a line in this cross product form is going to be r minus a crossed with b equals 0 that we have. And this is where a is a position on the line and b is a direction of the line. Now this is a really niche part of the course that I don't think has been asked about before, actually. I think maybe it's been in one mock paper, and it's the direction cosine ratios, and it is in there in the textbook, so I'm anticipating that it will come up at some point soon. So we have a vector, a position vector, and it's A, which is x, y, z. If alpha, beta, and gamma are the angles that it makes with the axes, in other words, the x, the y, and the z axes, then we can work out the cosines of these angles. And actually, geometrically, I kind of show this in a video, but the cos of alpha is just x over the magnitude of that vector. The cos of beta is the y component that we have over the magnitude of the vector, and cos gamma is z over the magnitude of that one that we have. And then similarly, what we know about this is that if you take these three things here, you can square them and add them, and they equal 1. And you can prove that to yourself by actually squaring these things and adding them, and you will see why it is equal to 1. So I'm just going to write down that cos squared alpha plus cos squared beta plus cos squared gamma is equal to 1. And then we start introducing some other letters to kind of simplify the way this looks. If L is equal to cos alpha and M is cos beta and N is cos gamma, then obviously you can just do a similar thing to this, which isn't that exciting, but it's L squared plus M squared plus N squared equals 1, just in case you kind of see it written in a different form here. And then interestingly, L to M to N, which are these cosine parts that we have here, they are in the same ratio as cos alpha to cos beta to cos gamma, because obviously that is just what they are equal to that we've said here, so they're in the same ratio. But actually, cos alpha, cos beta, and cos gamma, you can see here that they are in the ratio of x to y to z. So this gives us an interesting property that if we have a vector, the cosines of the angles that it makes with the axes are in the same ratio as the I, j, and k component. And I've got a video going through a couple of examples where they've used that. Intersection of planes, this is the FP1 method. If you want to use the CP1 method, then of course you can do, but there is just this alternative way of finding this. If you have two planes that are intersecting with each other, they will intersect along a line, and that line of intersection is going to be perpendicular to both of the planes. In other words, it is going to be perpendicular to the normal vector of the first plane and the normal vector of the second plane that we've got there. So because it's perpendicular to both of these planes, perpendicular the normals, to find the direction of that line, we can find that direction of the line, by doing the cross product of n1 and n2. That will give you a vector that's perpendicular to both of them, which is the direction of the line. And then you just need to find a common point on the planes, and you know our standard formula for the line of the equation of a line would just be r equals a point on the plane plus lambda lots of the direction of that line that we've got there. So you can see how that would all come together. But similarly, like I said, this is exclusive to FP1. You could use it in CP1 and CP2 if you want to. The shortest distance between skew lines, remember skew lines are not parallel and they don't intersect with each other. This is the FP1 method. If you go and refer to the Core Pure 1 Everything You Need to Memorize document, you'll also see that there is a Core Pure method for this as well. So the shortest distance, I find this one quite difficult to memorize, but if we have these two lines that look like this, we begin by doing A subtract C, and then this gets dotted with B cross D divided by the magnitude of B cross D. And just in case this is ever a negative thing, we just take the magnitude of the whole thing that we've got there. So it's pretty quick if you want to use that as a method, but I find this formula slightly harder to remember that we've got there. Okay, next part we're going to move on to is one of the biggest parts of FP1, which is conic sections. And I've split this up into the year 1 section and then the year 2 section that we have down here. So this is all in the formula book. I'm not going to spend too much time looking at this because you should have the formula book open when you are doing a conics section question so that you have it all here. So obviously we've got our standard form for the parabola and rectangular hyperbola. We've got parametric form. The eccentricity is actually not required knowledge for year 1. You're not going to need to use this or this, and you're definitely not going to need to know the directrix for this. They actually say that explicitly, that that's not required. But still, we need our knowledge of the foci for the parabola, or it's actually just a single focus here. The directrices, or it's actually a single directrix, and it has no asymptotes for the parabola. But we remember for the rectangular hyperbola, we have the asymptotes at x equals 0 and y equals 0. Now, introducing the year 2 ones, there's quite a lot of information here. Again, I'm not going to go through it in too much detail because this is actually just stuff that is in the formula book and you will need to use. They introduce the idea of eccentricity, which I will talk about a little bit lower down as well. Now, there is something that I do want to mention for this. if you're thinking about an ellipse that we've got here, the table is looking at an ellipse that is not written, but is an ellipse that is in that kind of shape. Okay, that kind of shape is where the major axis of the ellipse, in other words, the longest part of the ellipse, is along the x-axis. If we have it this way, where the major axis of the ellipse is along the y-axis, then a couple of things change with this. Instead of the eccentricity equation being like this, the a and b part have swapped over. So actually, instead of it being b squared equals a squared 1 minus e squared, it would actually end up as being a squared equals b squared 1 minus e squared that we have for that. And then similarly, if you think about the foci would normally be here and here, they've now shifted so that they're actually going to be on the y-axis, which means that the foci will also change. So I'm using the letter S here for the focus. You've probably seen that before. It would be on the y-axis, so it's going to start with a 0, and it would be plus or minus BE. Because remember, B is things on the y-axis, A is things that are on the x-axis, so that's why that's changed. And similarly, the directrices would also be different. The directrices normally are x equals lines. They're now going to be y equals lines. They're going to go from being vertical lines to horizontal lines. So please note that your directrices, if you have something that is this kind of form that we have here, it will be, the directrices will be a y equals plus or minus b over e like this. Now, how do you detect whether it's this version or this version that we've got here? Well, clearly, this one where it's a major axis is on the x-axis. The a parts are here, a and minus a, and the b parts are here, b and minus b. If your value of a is bigger than b, then it's this one. If it's this one here, then b is bigger than a. So I'll just quickly jot that down here. This is where a is bigger than b, and this one is where b is bigger than a. Obviously, if a was equal to b, it's a circle, and we wouldn't be coming up with that in this kind of thing. So things you might use in this, you're going to be using implicit differentiation if you're going to be using it in the kind of standard forms that we've got here. That would require some implicit differentiation. If it's parametric differentiation, you'd probably be using that whether it's in this parametric kind of form. And for the hyperbola, you're going to want to be careful about whether you want the question to be themed with trig or whether you want it to be themed with the hyperbolic identities for which one that you select. You're going to be using equations of lines, tangents, normals, all of that kind of stuff. And a quick note here is that the tangents and normals, there are some standard forms for the tangents and normals to the conic sections. I do not recommend memorizing them, and I have not put them on this document. As a result of that, you're going to need to just build them up yourself because they are very, very difficult to memorize. There's just so many letters going on. So what kind of tricks might you use in year 2 for this kind of stuff? Well, there are some algebraic tricks, particularly when you end up doing some stuff to do with loci. If you end up with something like p cubed plus q cubed or p cubed minus q cubed when you're doing something with one of these particular things that we've got here, where p and q are probably referring to some kind of parameters, well, you can actually do some factorizing with this. Now, the part that I always know is, okay, well, if there's a p cubed plus q cubed, there's always going to be a factor, and that factor is always going to have p plus or minus q. Now, the second part that we have that goes with this is always going to have, and this is the part I'm never always sure of, there's going to be a p squared and there's going to be a q squared like this. And then this part in the middle, you can kind of figure it out yourself, or you can want to standardly memorize it. There's a pq that goes in the middle and it's minus plus. And I suppose this one is also a plus that we've got there. But all you need to really know is that if you have p cubed plus or minus q cubed, there will always be a factor of p plus or minus q. And then it's going to be something that looks like this. And that can be really helpful because, again, we pull out this, not again, but we then pull out this pq that we have. And pq is often something that gets given to us in a question or we work out in a question. Similarly, p plus q squared is the same as p squared plus 2pq plus q squared that we've got there. And obviously PQ, well, not obviously, but this is useful if we know PQ, as is this part that we have, because it allows us to kind of do more algebra with these questions. So just wanted to point out these are a couple of algebraic tricks and techniques that you might find useful in these questions. So for eccentricity, I said we'd say a bit more about it. We use the letter S for the focus, D for the directrix, and P is a point that is on the conic, whether it's a parabola or a hyperbola or even a ellipse that we've got here. Now, I kind of remember it in this form that EPD equals PS. Obviously, the eccentricity is therefore PS over PD, but I tend to remember it in this form where it's just on one single line. And the way I do it in this one is that it finishes with PS. Silly memory technique, but you finish like at the end of an email or the end of a letter, you might write PS and then an extra kind of part. So that's how I remember that PS comes up at the end. And then there's this weird pattern for an ellipse that we've got here about what is PS plus PS dash, where S and S dash are the two foci that we've got there. Well, that is all equal to 2A that we have, where A is the distance from the origin to the edge of the ellipse that we've got there. And I think I go through in one of the videos the proof of that, but it uses the fact of EPD plus EP dash as well, and it just kind of all goes through geometrically with that. Okay, so the next part I wanted to look at is inequalities. Now, when you have inequalities, you always need to multiply through by whatever there's in the denominator, but it needs to be squared to ensure that it is not a negative. So I'm just going to write down, we're going to multiply it all through by the denominator squared. Then what you do is you find your critical values. This will make sense if you've already studied it. Let's see if I can spell it correctly. And then you sketch it and you solve it. And it's a very simple sketch. It doesn't need to be of the original graph, but it will be of the kind of quadratic or cubic or quartic or even quintic that there is. And factorizing is better than expanding. What I mean by this is when you juggle everything all around and make it equal to 0 and find the critical values, don't expand everything because you're going to get some crazy polynomials. Instead, try and factorize things together with keeping those common brackets. It is much better than expanding. Only expand if you really have to. The year 2 part, which is the modulus inequalities, you're going to try and just sketch the graphs if possible. If you have a graphics calculator, it's a bit of a game changer. Find the intersections by considering the positive and negative versions of the modulus that we've got there. I don't know why I've written negative as a word. I should probably have that written with a symbol just to make it a little bit more condensed. So you've got your positive and negative versions of the modulus part of the graph, and it's a bit trickier, those ones. So if you have a graphics calculator, that will put you in a really good position. T-formulae is a very small section of things that need to be memorized, but it's actually a pretty big topic, and it's, again, you've got to just do questions to be able to get good at this. So with t-formulae, we know that if t is equal to tan theta over 2, we can figure out what tan theta, sine theta, and cos theta are. Now, I remember what tan theta is equal to because it looks like the addition formula for tan, so that we end up with 2t over 1 minus t squared. That's because tan 2a is 2 tan a over 1 minus tan squared a. So you can see the similarities between this and this that we've got here. Now, sine theta, because this is the opposite and the adjacent for tan, sine theta always has the opposite, so there's going to be the 2t. And you could do Pythagoras with these to find out the third one, or you probably just remember that it's 1 plus t squared. And then cos theta is also going to be over 1 plus t squared. Remember that sine theta is the opposite over the hypotenuse, cos theta is the adjacent over the hypotenuse, so those hypotenuse parts need to be the same. And then the numerator for cos is 1 minus t squared, so we get that 1 minus t squared. All that stuff I was really just saying is that if we have that angle theta, we have 2t, 1 minus t squared, and 1 plus t squared. So if you find memorizing that triangle better, that might help you as well. Now for integration, which is kind of put in a different part of the textbook, we have the Weierstrass substitution. And all you need to remember for this is that if you want to do a substitution for the dx part that you have, it is the same as the sine part, but without the t in the numerator. It is 2 over 1 plus t squared dt. That will allow you to kind of do a substitution with integration that kind of takes you through to like a different kind of, just an integration question that is in terms of t. Now we're going to have a look at some stuff with Taylor series, which is obviously only in year 2 here. This is the formula that we have for the Maclaurin series, and the Taylor series is where it is not focused around 0. Now I think this is the first time I've shown you one of these where it says EQ. EQ means that it has recently been given within every exam question where it's needed to be used. They've printed it within the question, even though it's not in the formula book. And so this is the one that we've got for the Taylor series, and you can see how it's really similar to the one for Maclaurin, apart from where there's 0 there, A, and where there's x, there is x minus a. Now, there is a different version of this formula that you might find useful, and basically you'll notice to go from the one that's given to you, if you plus a onto x, if we just do that everywhere, we get a different version of this formula. So you still have your f of a. I'm going to plus a onto x, so it just becomes x. I'm going to plus a onto x, so I just get x squared over 2 factorial f double dash a like this. And with the r term, it just becomes x to the power of r over r factorial, the rth derivative with a substituted in, etc. Now, for solutions to differential equations, it is literally just going to be the same as the one that is given to you in the formula book, but just in case you want to see it in this kind of different language that we've got here, the solution would be that y is equal to y naught. So y naught is the equivalent to the value of y when x is substituted in, which is a in that particular one. And then instead of having x minus a in this part, we have x minus x naught. And instead of saying the first derivative in the function notation, we would just write it as dy by dx with x naught substituted in instead of a being substituted in. And the next one would be our x minus x naught all squared over 2 factorial. And it would be the second derivative, so that's d2y dx squared evaluated at x naught. And I'm just going to write etc. here because I can't be bothered to do it with the r term that we have as well, okay? So limits that we've got. Limits is a year 2 topic and it's spread across a few chapters, but I've put it all into one place here so that we can hopefully get a better idea, of what is going on. So they mostly behave as you expect. If you have 2 limits of 2 different functions that are both tending towards the same value, so in this case they're tending towards the value of c, then if you divide those 2 functions and find their limit, it is the same thing as just doing the limits to both parts separately. So I've called it P and Q to save me writing the word lim all the time. So that would be equivalent to just P over Q. If you're multiplying 2 functions, that is the same as just finding their limits separately and multiplying them. And if you're scaling a function, it is the same thing as just scaling that limit that we've got there. So that a effectively comes to the front. So it would be a multiplied by p. And then this is a really useful one that you need to know, is that we know that when you have the limit of x going to infinity of 1 over x or 1 over x squared or 1 over x cubed, etc., that always goes to 0. And I'm going to write etc. because of the fact it doesn't just have to be for the power of, for 1 over x squared, it could be like 1 over x to the power of 4. So creating things like that using division is a really, really useful thing for this. Now, L'Hopital's rule can only be done for these indeterminate forms where the numerator's limit is 0 and the denominator's 0, or if the numerator is infinity and the denominator is infinity. They don't both need to be positive. One could be positive, one could be negative, or they could both be negative. So L'Hopital's rule states that the limit of this thing is the same thing as the limit as x goes to a of their derivatives. So you can differentiate the numerator and differentiate the denominator, and the limit, if you can evaluate that, is going to be the same as the original question. And you can apply this multiple times if this thing is still in an indeterminate form that we've got here. So here are the indeterminate forms that I've mostly seen us come across. If we have 0 over 0, you've got 2 options, and the kind of question will give you a feel of what to do. If you've done Taylor, it's going to be pretty obvious that you're going to use Taylor for this part. When I say if you've done Taylor, I mean if it's like part A or part B. But if it's 0 over 0, you can use Taylor or you can use L'Hopital. If you have an infinity over infinity, that one is going to be something where you're going to want to use L'Hopital. Because Taylor's better when it's 0 over 0 because you get more things cancelling out. If you have something where 2 functions, the limit is a 0 for the first one and the limit is infinity for the second one, you can rewrite the original function, the f of x, g of x part, as f of x all over 1 over g of x. And this is because f of x has a limit of 0, g of x has a limit of infinity, and if we do 0 over 1 over infinity, that is the same thing as 0 over 0, which returns us back to this form where we can then either use Taylor or L'Hopital. So if you have something that starts off in this form, you rearrange it by dividing like this. If we have something that is an infinity minus infinity, so we have f of x minus g of x, and they both tend towards infinity, then what you want to do here is you want to combine them into a single term. Combine them into a single term. So maybe f of x is a fraction and g of x is a fraction. You want to kind of put those two fractions together so that it's no longer in this indeterminate form. It will probably go to one that we've already looked at here that you can then go through. Now this 1 to the power of infinity, I've only seen it come up in a particular proof, which is this proof that sometimes has occurred here. If you have 1 to the power of infinity, the way that we deal with this is we rewrite it as e to the power of ln of 1 to the power infinity, because obviously e to the ln, they cancel out, so this is equivalent to this, and then we can pull that infinity to the front so that we get e to the infinity ln 1, and that gets used when we're trying to prove this thing. Now, if you're not sure what I'm talking about here, in one of the playlists about limits, you will hopefully remember this proof and you can look through the notes that I've done with this, where you're trying to prove that this thing goes to this. So when you do this proof, you have to use this fact. You also have to use the fact that the limit of e to the f of x is the same thing as e to the limit of f of x that we've got here. So kind of makes sense that the limit of this thing, we're only really concerned with what's happening to that f of x. Now this proof, I was considering putting it in this video, but it is so long and complex. We just really hope that it doesn't come up in the exam. I don't think it's come up so far, and I don't see it really happening, to be honest. I think it's a complex one. Okay, we've now got Leibnitz's theorem. This is all to do with differentiation, of using the product rule multiple times. Of course, this is the year 2 topic that we've got. So if y is equal to uv, where these are a product of two functions, then the nth derivative, which I'm writing with y with an n in brackets there, is the sum from k equals 0 to n. We have the binomial coefficient where we have n and k. We then have u, this is not to the power of k, but this is to like the kth derivative, and we have v to the n minus kth derivative, okay? So what this means is that the orders of the derivatives, here we have k and n minus k, they will always add to n, the derivative that you're trying to find, and n, k at the beginning are literally the binomial coefficients. So I think the best way of me trying to demonstrate this is to remind you with an example. So the fourth derivative of y, well, the binomial coefficients for the fourth derivative will be 1, 4, 6, 4, and 1. So I'm going to start off with u would be to the 0th derivative. Now the 0th derivative is just u. We would then have v, and it would be to the fourth derivative. Notice how this looks like it's a 1, but it's not. This is just a 4 and a 0. So the next part would be a 4 with the u differentiated once and v differentiated 3 times. We then get the 6 with u differentiated twice and v differentiated twice. The 4 with u differentiated 3 times and v differentiated once. And then just for the last part, we're going to get u differentiated 4 times, and we're going to get that v that goes with it as well. Okay, so we've got all of these. The derivative orders are always adding up to 4. Sometimes people forget to do that. When you see it in a table, it just is really obvious how these things all kind of pull together. Okay, we are nearly there. We are at probably my least favourite part of FP1, which is numerical methods that we've got. So Euler's method. Euler's method, this part is given to you in the exam question, but what you will find is the iterative, the rearranged version of this is more useful, which we're going to fill in here. So we're basically going to make the y n plus 1 as the subject. Like I've said, every time they've been giving these questions recently, this always appears to be printed. So we get that y of n plus 1 is approximately equal to y of n plus h lots of dy dx evaluated for the nth one as you're doing this iterative process that we've got here. The midpoint formula that we have is a similar thing. I'm going to rearrange it to make y n plus 1 the subject. So that one is just going to be y of n minus 1 plus 2h lots of dy by dx n. And so we've got these iterative formulas that go with this. If you are required to use the midpoint method at one point, you first of all are going to need to use Euler's method, and then you're going to need to use the midpoint method. So often you're going to do one of those and then one of these. Now, if you have a second order differential equation, you obviously need to use the second order method. Again, this would be printed for you in the exam question. So we still want yn plus 1 as the subject because it's an iterative formula that we've got here. This is going to be 2, which way round do I normally do this? Good. I do 2yn minus yn minus 1 plus h squared lots of the second derivative that we've got here like this. And this is the rearranged one. They give you this. I think this one is more useful. Now, if the second derivative that you're trying to do the numerical methods on has no dy by dx, for example, if this was the equation that we were working on, it has no dy by dx, what you're going to do is you will do Euler's method to begin with, and then you will use the second order method afterwards. If the second derivative has a dy by dx term, for example, this one is the same as this, apart from y has been multiplied by dy by dx, you're going to use the midpoint method, and then you're going to use the second order method, and you will combine these two equations together using simultaneous equations. Now, this is going to sound like jargon unless you go and do a practice question and you try and then see how this is all coming together, because I've tried to make this topic that I think is quite a confusing one have a bit more of a solid method to it. So do use this as you're going through some of these questions. Now, Simpson's rule that we've got here is for doing integration that we've got. And I have this ridiculous cheesy way of trying to remember this. I know that pi is equal to 3.142 to 4 decimal places. That's just something I know because when I was doing maths, I didn't have the pi button on a calculator, so I'd always have to put it into 4 decimal places. Now, where is this coming from? So if you want to do Simpson's rule, and I guess I should really say this is what it's approximately equal to rather than is exactly equal to, you get the third that we have here. I'll explain where it comes in a second. And it's a third of the height, a bit like the trapezium rule. You're then going to have the endpoints plus 4 lots of the odd values plus 2 lots of the even values. Now, what was the point of me talking about pi being 3.142? Well, the 3 reminds me that it's the third. The 1 that we have here just reminds me of the fact that the endpoints get multiplied by 1. The 4 is for 4 of the odd values, and the 2 is for 2 of the even values. And it's always worth remembering when you do this that the endpoints, the first part that we have, will always be starting off with like y0. So the odd values are like 1, 3, 5, 7, and the even values are the ones that are in between all of that as well. Again, it will make more sense if you look back at the notes and see it with an example. So we're on to the last part here, which again is quite a wordy part for me to explain. I'll do a couple of examples here to try and demonstrate one of the points. So first of all, when you're doing reducible differential equations, I want you to ensure that the letters are treated as variables and not constants, which means you're going to need to use implicit differentiation and the chain rule a lot that we've got here. I want you to carefully check what you are differentiating with respect to as well. Because if you need to differentiate with respect to, this is with respect to, a different variable, you're going to need to use the chain rule. And I think this is one of the sort of trickiest parts that we've got here. So I'm going to try and demonstrate this with a couple of different approaches. If we wanted to differentiate dt dx with respect to y. So this is quite weird because we're trying to differentiate this thing with respect to a totally different variable that doesn't appear here that we've got. So I'm going to just translate that into kind of a differentiation statement. I am trying to differentiate dt dx with respect to y. So in other words, I am trying to do d by dy that we have here to dt by dx. Well, I can't do that, but I can differentiate dt by dx with respect to a different letter. I'm allowed to differentiate it with respect to x because it's already been differentiated with respect to x once. But to counter this dx here, I'm going to have to multiply by a dx, and I'm going to have to maintain the dt that was, oh, not the dt, the dx by dy, excuse me. I'm going to have to maintain that dy that was here. Because if these things cancelled, the dx is cancelled, the dy would still be here, and these two statements are equivalent to each other. So now I can actually evaluate the dt dx differentiated with respect to x, where we know that that is going to be the second derivative like this. That's the second derivative like this, and it is still getting multiplied by dx by dy. Now, there's another way that you could think about this. If we let u equal dt by dx, and I wanted to differentiate it with respect to y, then I could say that du by dy is just going to be the same as du by dt. Yeah, is that what I want, du by dt? No, I want du by dx because I'm differentiating it with respect to x here. So I get du dx multiplied by dx dy that we've got here. And then I've still got this dx dy that we've got. I now just need to find what du dx is. So du dx is just this thing being differentiated with respect to x that we have. So we get the same thing of the second derivative of t with respect to x multiplied by dx dy. So you've either got this choice of using a substitution and introducing another variable, or using this kind of technique that we've got here. Personally, I'm used to doing this kind of one because I think introducing another variable can be quite confusing, but I've given it there to you as an alternative. You saw me hesitating here. I probably shouldn't have hesitated. I should have realized that I wanted to put a du by dx because I have a u that has already been differentiated with respect to x. So it kind of made sense that I wanted to put x there rather than t, because that's already kind of like bound up in it as well. And then once you've transformed it, you obviously refer back to your core pure 2 techniques, because once you've transformed it, you've still got to do a differential equation, which we know is quite a time-consuming and tricky process. So that's just the first stage of those bits that we've got. So that is everything that you need to memorize for Further Pure 1. I think Further Pure 1 is one of the heaviest of the option modules. I think there's a lot to memorize, but there's a hell of a lot of skills that go within all of this kind of stuff as well. So hopefully that was useful. Do let me know if there's anything you need to know any more about. But otherwise, good luck with your revision, and I will hope to see you in another video soon. Thanks, guys. Bye.